Okay, we're going to continue on here. Some chapter 15. How about that one? I think. So obviously, we were talking about solutions in this chapter. We talked about really some concentration type units that are important. We did some percent concentrations, percent mass to mass, which is our mass of our solute divided by our mass of our solution times 100%. As we talked about with this particular one, you do want to be careful of the bottom aspect of it. Remember, again, a solution is a solute and the solvent together. And again, in a lot of these type of problems, they oftentimes will give you that information separate from one another. So you want to make sure that you're not just dividing by the larger number, which might be the solvent. You want to make sure that you actually do get the solution. There's some similar ones, percent volume to volume, which is the volume of the solute divided by the volume of the solution times 100%. There's also percent mass to volume, which is our mass of our solute divided by the volume of solution times 100%. We then talked about, in addition, if you do have sort of these percent compositions, not really, or percent concentrations, if you want to use it in a calculation, a lot of times it's good to kind of turn it into a conversion factor. So if you had like a 2.75% by mass sodium chloride solution, you could just assume 100 grams. So like 2.75 grams of sodium chloride and 100 grams of solution. Or you could use it like a conversion factor and flip it around the other way with 100 grams of solution would contain 2.75 grams of sodium chloride. So sometimes it's easier to just kind of convert it into a conversion factor. You could also just plug and chug into the equation as well and solve for whatever you're looking for. It's really the same math and it should come out the same regardless of which way you do it. We then talked about really the main type of concentration that we use for solutions, which is molarity, and that is moles per liter. And it is really like a formula, and you should be able to solve for any of those three things. And it's very common in chemistry that we do solve for any of those things. If we want liters, that would be our moles divided by molarity. If you want moles, which is a very common sort of calculation, like you'll do today in lab as well, liters times molarity is also the right way to rearrange it. We also talked about that if you are doing some type of calculation like this guy here, or really anything with just the molarity equation, the volume really should be in liters so that you do get moles at the end. We talked that you could, if you wanted to, multiply milliliters times molarity. The difference, though, is you do not get moles when you do that. You get millimoles, and that is, again, going to be about a 1,000-fold factor difference if you do that, and you're going to be off with your calculation. I would say probably 99.99% of the time, you're probably going to be looking for moles when you're doing some type of calculation like that. So just make sure that it is in liters so that everything will be correct when you're doing it. Now, in addition, when you're using molarity in a calculation, it's a really good idea to get rid of the big M and really put both of the units that actually are part of molarity in there. And it will always stay with the moles part, the number. So that would be 2.75 moles per liter, and it's always 1 liter. And you could also use molarity just like a conversion factor. You can use the moles over the liters. You could flip it around if you needed to use it in sort of the opposite direction. Again, as we talked about last time, if you take more of a dimensional analysis approach in a lot of situations, you may not even have to worry about remembering the formula or rearranging the formula. You could just think about, again, it's getting rid of the units you don't want, keeping the units that you do want, and you'll kind of do the math for you without having to maybe remember a formula or rearrange a formula. So that's really important. Again, a lot of people always screw this up because they just think about big M, like I said last time, and it's like moles is all they have in their head. They don't know anything about the liters part, the volume part, or where any of that stuff is. And they oftentimes just really kind of mess up the calculation very commonly. In addition, with molarity, we also talked about the idea that when you have an ionic compound that is a solution, really what you have in that solution are really just ions that are floating around. And sometimes we're interested in perhaps maybe not the molarity or concentration of the entire sort of ionic compound, but we're interested maybe in the molarity of just the ions that might be floating around in the solution. So we can relate molarity to sort of the individual ions. And again, if we had something like barium chloride, that would break apart into a barium ion and a chloride ion. And you actually get two chloride ions in this case. And if the concentration of the entire thing was 2 molar, really the quick way to figure out the concentration of each of the ions is just to do really kind of like a stoichiometry sort of relationship. It is a 1-to-1 relationship between the whole thing and the barium ions, which means you basically just take 1 times the concentration, or the concentration would remain the same. So we would have 2 molar would be technically the concentration of the barium ions that were floating around in that solution. When we look at the chloride, it's a 1-to-2 relationship. So we do have to take that into account, and we would take 2 times the 2 molar, and that would give us 4 molar would be the concentration of the chloride. Again, they're not additive, but it just visually, if you look at it right, you basically got 1 barium and 2 chlorides floating around. So it's really twice as concentrated, right, with chloride ions floating around than it is with the barium ions. And you can see that reflected in the concentration. It's twice the concentration of the single ion that's floating around. We also talked about at the end there dilution. And dilution is really when we add more solvent. And although water is a very popular solvent, it's not always sort of the solvent of choice. But a lot of times when people talk about dilution, they talk about just adding more water. And when we're doing that, what happens is we think about molarity, which is really the moles of the solute divided by liters of solution. And once again, the solution is our solute plus our solvent. When we go about doing some type of dilution and the only thing we're adding is more solvent, which is here, that means that really in terms of this molarity equation, this guy gets bigger, which means when you divide it out, the molarity will go down in that case. And that's why the molarity goes from a higher concentration to a lower concentration, because you're really increasing the amount of the solution and really the amount of the solvents particularly. One important thing is it is the moles of the solute that basically remain the same before and after dilution. So your moles of your solute, which is really the stuff, by the way, in the solution that is basically reacting. It's the solute that really goes through the reaction, and it will stay the same. So again, we only will really see a lowering of the concentration when we do a dilution. And that's important, and you'll learn more about that as well as you get into perhaps 1B. Sometimes when you do calculations involving mixing volumes together, a lot of times we look at the moles because they say constant. They don't change, rather than looking at the molarity as we're doing it as well. Now there's an equation that goes with dilution, which is M1V1 equals M2V2. This is sometimes referred to as the dilution equation. There's also a more generic version of it, which is C1V1 equals C2V2. Because molarity is probably the most common unit of concentration, most people roll with this one, which is the molarity times the volume equals the molarity times the volume. This is before your dilution. This is like after your dilution. So here C is just generic for concentration. And what that means is you really could use this sort of equation with any type of concentration unit. You could do percent mass to mass on both sides, percent volume to volume on both sides. But again, molarity is the most common one. This is the one formula that we talked about when you're going into this dilution equation here, that if you chose to do so, you could leave the volume in milliliters and it will work out okay. And again, if, for example, we're solving for V2, which would be M1 V1 divided by M2, and you had molarity, milliliters, molarity. Molarities cancels. It just means that your volume will be milliliters when you solve for it. Now, if you're solving for something like M2, M2 would be M1 V1 V2. Again, if you did molarity, milliliters divided by milliliters, they will cancel out and you'll be back to molarity. So if you choose to do so, you can definitely, and it's very commonly used in a dilution equation, leaving the volume in milliliters and times it by, it will work out okay. If you want to convert to liters, you can as well. The only difference is your volume that you solve for will be the liters of the rather than milliliters. And once again, it really does work out because, as I said before, when you take milliliters times molarity, you get millimoles. And then if you divide those millimoles by milliliters, the millis cancel and you're back to moles per liter, which is molarity. So that's why it does work out that way. But again, if you're individually using molarity and volume, definitely convert it to liters because you want moles and not millimoles. And you, again, won't be off by that factor. Any questions on that there? All right, so I think we left off with perhaps this example that I just wrote all over. So why don't you give it a go and see what you come up with? Or let's take a look at it together, actually. Let's take a look at this one here. We're taking, we want to know what volume of 19 molar sodium hydroxide is needed to use to prepare 1 liter of 0.15 molar sodium hydroxide. So first off, we're really going from sodium hydroxide to sodium hydroxide. So there's no reaction. The only difference is the molarity is changing. So basically what we have going on here is we got this bucket here of 19 molar sodium hydroxide. And what we want to do is make a new container that has a volume of 1 liter, which is like 1,000 milliliters, and has a molarity of 0.15 molar. So this is definitely a dilution type of formula here. We would use our M1 V1 equals M2 V2. Typically speaking, the ones are the more concentrated and the less concentrated ones are the twos. It truthfully doesn't matter as long as you keep the numbers that go together. So I'm going to call this my 1. I'm looking for V1 in this case. And this would be my V2, and that would be my M2 in this case. So in this case, we are solving for V1, and V1 would equal M2 V2 divided by M1. Putting in our numbers here, we got 0.15 molar. Our V2 is 1 liter divided by our M1, which is 19 molar. Our molarities here will cancel out. And in this case, my volume's in liters, which means my answer will be in liters as well. So 0.15 divided by 19 gives me 7.89 times 10 to the minus 3 liters. And if I convert that into milliliters, by timesing it by 1,000, gets me 7.89 milliliters. So that number represents basically the amount of the more concentrated sodium hydroxide that you need to take out. So what we would do is we would take out of this more concentrated bottle 7.89 milliliters of the more concentrated sodium hydroxide. I want my volume here to be 1 liter when it's done. Should I add a liter of water to this? The answer is no, you shouldn't, because then you would have like 1 liter and 7.89 milliliters, right? So you would have too much volume here. So we do want our final volume to end up exactly what we're shooting for. And I'm going to use the milliliter version of it, which is 1,000 milliliters. So to find the volume of water that we need to add, typically that is V2 minus V1. We know that we want to end up at 1,000 milliliters. We have already put in there 7.89 milliliters of the solution. So if we take 1,000 minus 7.89, that's going to get us something like 992.1, we'll call it milliliters of water. So what we would need to do to make the solution is take out about the 7.9 milliliters of the more concentrated solution. We would add in about 992.1 milliliters of water in that case. We give it a good mixy, shaky, maybe not so much shaky, mixy. And at that point, we should then have a total volume of 1 liter or 1,000 milliliters. And that solution should then have a molarity of 0.15 molar. Any questions on that there? So typically speaking, if you solve for M1, that's usually the concentration of your more concentrated solution. If you solve for V1, that's typically how much of the more concentrated solution you need to make your new solution. And obviously M2 and V2 are your dilute guys, typically the molarity and the total volume there. Any questions on that one there? All right, why don't you try one then? Why don't you try this one? What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? Okay, let's take a look. So kind of same setup here, calcium nitrate, we just have some different concentrations. So this is a dilution situation. So once again, we have, in this case, a more concentrated bottle here of calcium nitrate. We want to eventually make here 500 milliliters of a 0.25 molar solution. So we're going to use our M1 V1 equals M2 V2. Here we will solve for V1, which is the only thing we do not have. And again, I'm going to leave it in milliliters because it will work out okay here. So my molarity 0.25 molar times it by my 500 milliliters divided by my original molarity, which is 5. And at this point, the molarities cancel. And again, that's why it works out okay. I'll end up with milliliters in this case. And if I do that, I believe that's a 25, if I'm not mistaken. 25 milliliters in this case. Once again, that is 25 milliliters of the calcium nitrate solution, the more concentrated one. So I'm going to reach into my more concentrated bottle. I'm going to transfer over here 25 milliliters of it. I do want a final volume of 500 milliliters, and we want to make sure we do answer the question, which is actually a very common question in dilution problems, which is how much water do you need to add? So again, to find the volume of water, typically speaking, that is V2 minus V1. So our total volume is 500 milliliters. We've already put in there 25 milliliters. So that's going to give us a net of 475 milliliters of probably deionized water that we're going to put in there. We'll put in there our 475 milliliters of water, giving us a total volume of 500 when we all mix it together and a concentration of 0.25 molar. Any questions on that there? Question on dilution. So I say it's a very common mistake that sometimes people make again is not answering the question like when asked how much water that you need. And also, again, with the volumes and stuff like that, making sure that they are the same units and not different units and stuff like that. Any questions on dilutions? All right, the next unit we're going to then talk about is everybody's favorite, which is stoichiometry. So we've done regular stoichiometry problems, kind of grams and moles. We've also done gas stoichiometry problems. So of course we should do some stoichiometry problems that involve solutions. The good news is, as we've talked about with other stoichiometry problems, that's pretty much the same steps. So all the steps are really the same. So we have our basic steps for stoichiometry problems of we always want a balanced equation. We want to, again, convert to moles. And whenever we do any type of stoichiometry problem, we also want to make sure that we double check or make sure if it is or is not a limiting reagent problem. So with gas stoichiometry, solution stoichiometry, regular stoichiometry, you could always have a limiting reagent type situation. A reminder that it is a limiting reagent situation when you have enough information given to you in the problem that you could essentially calculate the moles of each reactant. So if you have a way right from the problem that they give you based on the information given to you that you could get the moles of each reactant, then it is a limiting reagent problem, and you do have to calculate that. As we talked about, it has to be some type of calculation to figure out which one is the limiting reagent. So you want to always keep that in mind. Once you know it is or is not, then we roll into our normal steps, mole to mole relationship from the balanced equation, and then our moles to some other unit. So very much like sort of gas stoichiometry with solution stoichiometry, we kind of get the moles a lot of times in step number 2 from using our molarity equation. And here our moles would be liters times molarity. And for sure, you wanted it definitely in liters in this case. You also can, in a solution stoichiometry, have a regular one where you use grams to moles like normal and the molar mass as well. Also on the back end here on step number 4, we also will use molarity a lot. You may have at the end the moles from your stoichiometry part, and maybe you are given the actual volume. So if you have both of that information, you could actually just solve for the molarity of something. You might at the end have the moles and the molarity given to you, which means from that information, you could actually solve for the volume or the liters that would be there as well. So usually step number 4, a lot of times, you'll kind of incorporate molarity as well. For example, in titrations like you're doing today, you incorporate kind of molarity at both spots, kind of step number 2 and step number 4 in the calculation. You kind of do them at both of those places. Sometimes as well, though, in a solution stoichiometry problem, it may end like a normal one, which is you take the moles, the molar mass, and figure out grams. So that's also a possibility as to how these guys should end. Any questions on there? So let's take a look at one here together and kind of go through the different steps that we want to look at when we're doing this type of problem. So we want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of a 0.2 molar solution of barium nitrate to precipitate out all the barium as barium sulfate. We also want to calculate the mass of barium sulfate that's formed. So this is a 2-for-1 type question. There's 2 different problems sort of happening. But regardless here, it's all stoichiometry, which means pretty much we need an equation. So we want to start with the equation. And in this case, we don't have it given to us. We do have to write it. So we want to calculate the mass of sodium sulfate. Sodium is +1, sulfate is -2, which means when we put those guys together correctly, we should get an Na2SO4 because we need 2 of the sodiums. It's going to react with barium nitrate. Barium is +2, nitrate is -1, which means when we put those guys together correctly, they equal 0. This is what we should end up with. Once you have these 2 really ionic compounds here, that also should tell you this is a double displacement reaction, which means they're going to switch partners. I'm going to do that move right there. Remember, as we talked about, if you need to write the equation, you want to make sure that you first get on the right-hand side of the arrow all the correct formulas and then balance it. So you want to make sure you get the right formulas down first. That means the sodium, which is really +1, and the nitrate, which is -1, will come together to make NaNO3. It will not make Na2NO3, yes? So don't balance it. You should put it together correctly first. The barium will come together with the sulfate. Barium is +2. Sulfate's -2, which means you just need 1 of each of those guys. And that will give you the proper formula. Again, once we have the proper formulas down, now you should balance it. And in this case, we do need I think we just need a 2 right about there. We'll balance it, I think, in this case. Any questions on how I got the equation or anything like that? Okay. So I'll get rid of some of this extra stuff. Now that we have our actual equation, let's use it to figure out what we're looking for here and what was given to us. So first off, we're looking for the mass. So we're looking for the grams of sodium sulfate. So we are, bless you, we are looking for this guy here. We are given that we have 250 milliliters of this guy, and he has a molarity of 0.2 molar. And lastly, we are also looking for the grams of this guy as well. So we got a couple different problems kind of tied up into here. So first off, is this a limiting reagent problem? This is not a limiting reagent problem because we only have the ability to get the moles from this guy, right? And we can't, obviously we're looking for the other guy, so it can't be a limiting reagent problem. So this is really just a basic stoichiometry problem. So we're going to do it here. I'm just going to kind of erase that so I can have some room to write. So we're going to start with step number 1, which we did. Step number 2 is to convert what they gave us into moles. And in this case, we're actually going to use molarity to do that. Our molarity, again, is moles per liter, which means our moles is going to be liters times molarity. That means that we do need to convert our milliliters into liters. That is a very common conversion. We do a lot with solutions. And a reminder that that is 1,000 milliliters is 1 liter. Right? Those cancel, gives us 0.2500 liters. The other important thing we talked about again is we want to really get rid of this big M, and we want to convert it into a usable conversion factor like 0.2 moles per liter, and that is how we're going to use it. So I'm going to use both of those guys and set it up dimensional analysis way to get my moles of barium nitrate. And that's going to be my 0.25 liters using my molarity as like a conversion factor. Opposites cancel, so moles up on top, liters on the bottom here. Liters will cancel, and that will now give me here 0.25 times 0.2, 0.05 moles of barium nitrate. Any questions on that so far? So this is very much like a normal stoichiometry problem. Instead of using grams and molar mass to get moles, molarity and volume to get moles, which is a very common way of doing it. Now it becomes really just a stoichiometry problem. So I'm going to do step number 3 here, and I'm going to go to this guy first. So we're going to go this way here first. So step number 3 is our mole to mole relationship. And we can see from the equation that for every 1 mole of sodium sulfate, you get 1 mole of barium nitrate, right? So that's a nice relationship. It's a nice 1-to-1 relationship here. So we're going to take our moles of barium nitrate. We're going to use the stoichiometry from the equation. 1 mole of barium nitrate gives me 1 mole of sodium sulfate. I think I could do that math there. That's going to be 0.05 moles of sodium sulfate. Yeah. Any questions on that there so far? What's left is we're looking for how many grams. So this is going to be a normal mole to gram conversion, which means it's going to be the molar mass from the periodic table to do that. So we got the molar mass here of Na2SO4. That's going to be 2 times our 2299 plus our 3207 for our sulfur plus 4 times 16 for our oxygens. It's going to give us a molar mass of this guy of looks like 142.1 grams per mole. So that would be our 4th step here to answer one of the questions that was asked. 0.05 moles of sodium sulfate. And we'll put our grams up on top, 142.1 grams per mole. Moles will cancel. And we will end up with here. Looks like 7.1 grams of sodium sulfate would be needed to be mixed in with our 250 milliliters of solution. Any question on that part? Now, we did have a second sort of problem in this one. So the next thing that we're going to do is really figure out from here to here and see what we got going on. The good news is it's all the beginning steps are the same. So we already did 1, we already did 2. We could actually just pick it up right here after step number 2 and roll with step number 3, which is just the other mole-to-mole relationship in this case. So I'm going to pick up with the second step number 3, which is I'm going to take the moles of my barium nitrate that we already calculated. And I'm now going to do the mole-to-mole relationship between barium nitrate and our barium sulfate. And in this particular case, it also happens to be a 1-to-1 relationship. So from the equation, we see that for every 1 mole of barium nitrate that we put in there, we get 1 mole of barium sulfate out. The moles of the barium nitrate cancel, giving us 0.05 moles of barium sulfate. The last thing that we need again is grams. So we will need the molar mass of barium nitrate in this case. Barium is, what is that, like 137, I think. Yeah, 137.3. So barium sulfate, 137.3 grams per mole, plus our 3207 for our sulfur, plus our 4 times 16. I'll go through there. Gonna give us here 137.3 plus 3207 plus 4 times 16, 233.4. So we'll use that as our 4th step here, 233.4 grams per mole. And that will get us here then 11.7 grams of barium sulfate would be created in this reaction. Because that is a product, that would also be the theoretical yield, right? So that would be our theoretical yield in this case. Any question on those steps? By the way, if that wasn't enough way to do it, you could, if you wanted to as well, picked up with these moles and did the mole-to-mole relationship between those guys, and it would come out the same. So that's the nice thing about stoichiometry. You've got the moles of one thing, doesn't really matter what it is, you could relate it to everybody else. So you could have went back and just used this sodium sulfate if you wanted to, did the mole-to-mole relationship to the product, you'll get the same answer. Any question on any of those steps? So really kind of the same stoichiometry steps, just incorporating molarity there in step number 2. Like I said, step number 2 very commonly, and that's where you do it, and also step number 4 as well. All right, why don't you try one then and see what you come up with here. If there is one somewhere, here we go. Calculate the mass of calcium carbonate that forms when you mix 25 milliliters of 0.1 calcium nitrate with 20 milliliters of sodium carbonate. I'll give you some info that might be helpful. Calcium 4008, carbon 12.01, and oxygen 16. All right, so take a few moments, work through the steps and see what you come up with here. We want to calculate the mass of calcium carbonate. We're mixing calcium nitrate and sodium carbonate together. So clearly we're going to need an equation. So we're going to start with our calcium nitrate, which we are then mixing with our sodium carbonate. And once again, this should set yourself up for a double displacement type situation. Again, the calcium and the carbonate, the sodium and the nitrate in this case. Once again, we want the proper formulas. So our calcium, which is +2, and our carbonate, which is -2, will come together to make our calcium carbonate, which is our solid, and our sodium, which is +1, and our nitrate, which is -1, will again come together like so, no extra 2's in there. The 2 should end up in the front now that we can balance it up at this point. Any questions on the equation there? All right, now we got the equation, which is really number 1, and I killed a 3 there as I was going racing. Let me put that back. There we go. Now we could take the information that was given to us. So in this case, we do have 25 milliliters of this guy, and it is 0.1 molar. We also have 20 milliliters of this one and 0.15 molar. And we are looking for how many grams in this case, right? So again, I'm going to get rid of some of that so I have somewhere to write. First off, is it a limiting reagent problem? The answer is it is a limiting reagent problem because we could get moles from our molarity and volume, and we could get moles also from our molarity and volume. That's the moles of each of our starting material here, which tells us we do have to take into account the limiting reagent aspect of it. Any questions on that there? All right, so the stoichiometry part is still the same. We're going to go 1 here, which is already done. We're going to convert into moles. We could get 2 moles in this case. So we are going to convert our volume into liters. We're going to divide by 1,000. So when we do that for our first one there, calcium nitrate, 0.025 liters. That's converting that into liters by dividing by 1,000. We're going to also get rid of the big M there and turn it into a usable sort of way. And we're going to go with 0.1 mole per liter of calcium nitrate. Liters here will cancel, and that's going to get us there 0.025 times 0.1. 0.0025 moles of calcium nitrate. We'll do the same thing here for our other one. We're also going to convert this into liters by dividing by 1,000, or move the decimal place 3 places to the left, 0.02 liters. Also going to get rid of the big M there and convert it into a usable conversion factor, 0.15 moles per liter of our sodium carbonate. And that's going to give us 0.003 moles of sodium carbonate. So remember that this is sort of our starting amount, and we do have to do the limiting reagent, which again is a calculation. So in this case, our limiting reagent calculation, I'm going to determine how much sodium carbonate is needed. So I'm going to take my moles of calcium nitrate. I'm going to do the mole to mole relationship between calcium nitrate and our other reactant, which is a 1-to-1 relationship between those two. So 1 mole of calcium nitrate gives us 1 mole of sodium carbonate. That means that we will have 0.0025 moles of sodium carbonate is needed. In this case, remember, we want to compare it to what we're starting with. Do I have enough in this case? I do have enough. I have 0.003 to start with. I only need 0.0025. So I do have enough. So once again, that means that this guy is going to be our excess reagent, and it is going to be the calcium nitrate in this case that's going to be our limiting reagent. Remember, that's not always the smallest number. Yeah, so you got to actually do a calculation to determine it. Any questions on that there? Once we've determined that it is our limiting reagent, the rest of the calculation is just going to be our stoichiometry calculation. We're going to start with our limiting reagent, which is our 0.0025 moles of calcium nitrate. We will now do the mole-to-mole relationship between that and our product, which looks like it is a 1 mole of calcium nitrate to 1 mole of calcium carbonate. So that's not too bad either. 1 mole calcium nitrate, 1 mole calcium carbonate. Moles of calcium nitrate cancel, gives us 0.0025 moles of calcium carbonate. We do want grams, so the last thing that we need here is the molar mass of calcium carbonate to calculate that. So that's going to be 4008 for our calcium plus 12.01 for our carbon. And in this case, we have 3 oxygens at 16. Going to give us here 4008 plus 12.01 plus 3 times 16. Looks like 100.1 grams per mole. We'll use that as our final sort of conversion factor here. I'll try to squeeze it in there maybe. 100.1 grams per mole. The moles will cancel, and we will end up with here 0.25 grams of calcium carbonate would be formed in this case. And once again, that would be our theoretical yield in this particular case as well. Any questions on those steps there? So these couple examples, again, demonstrate a couple things. We can incorporate molarity into our stoichiometry and still kind of finish it up the same way as a normal problem. We also can still have, as I mentioned before, a limiting reagent situation that's occurring. So let's talk about another very common solution stoichiometry situation that occurs, and that is with titrations, like you're going to do today in lab. And titrations oftentimes are acid-base titrations, and a lot of times in acid-base titrations, we get an overall reaction that's occurring that is a neutralization reaction. And if you remember, one of the reasons why a reaction takes place is the formation of water, and that's essentially what's going to happen in this case. A reminder that whenever you take any type of strong acid plus a strong base, you will basically get a salt and water that is formed. Water obviously is H2O. And in the case of a strong acid and strong base, the H plus comes from the acid, the OH minus comes from the base, and that is how we get our water. The salt's an ionic compound. So it basically is whatever ions are left. So if you had a little HCl like you're going to do today, plus a little sodium hydroxide action. Again, it really is a double displacement reaction happening. H will go to the OH, the sodium will go to the chloride. You'll make sodium chloride, which is your salt, and you will make water there from basically the double displacement reaction that's occurring. So when we do something like a titration like you're going to do today, there's a few things about that, and let's talk a little bit about that. And let me do some award-winning bad drawings here, so you'll see in real life it'll look just like sort of these drawings, maybe. So when we do a titration, typically speaking, we usually will have 2 types of solutions. We usually will have what is sometimes referred to as the known solution. And what that means is you pretty much know everything about that solution. So in the case, for example, of a titration, you know the molarity of that solution. You also know the volume of that solution. So you pretty much will know everything about that solution. So in your case, when you do the titrations today, that's going to be your sodium hydroxide that you're going to be using. It's going to be like your known solution. You also will typically have an unknown solution. And in an unknown solution, you really don't know everything about it. So maybe all you know is the volume, or maybe all you know is the molarity of it. You don't really know both of those things for sure. There's something that you don't know about it and you're trying to find it. So we use stoichiometry when we do a titration to figure out really what's happening with the unknown solution based on the known solution. And when we do a titration, you use a burette, which, sort of looks like that ish. Close your eyes. And a burette has what's referred to as the stopcock. That is the thing that opens and closes it. Yeah. So when you're filling it, make sure it's closed, by the way. It's in that position, parallel to the cylinder. It's open. So make sure it's closed when you do fill it. By the way, we fill a burette here from the top. Usually like a funnel would be a good idea probably as well. So we fill it from the top and obviously we let it out from the bottom. So when we look at the burette, something weird about it as well, in a sense, is the volume actually does increase as you go downward. And if you have like your volume level right about there, that is like 1.50 milliliters. It is not 2 point something. It's really important that you take a proper reading when you do that. When you usually do go to 2 decimal places when you do a reading. And when you use a burette in a titration, you always want to take an initial reading before you add anything. And you usually want to take a final reading when you're done with your sort of experiment and you reach what's known as the equivalence point. And the reason you want both of those readings is you could actually get the volume that was added by just subtracting those two. So if you do a titration and you only have one reading or no readings, you kind of wasted your time. You're just like adding stuff. You have no idea how to do the calculation. So you always want to take an initial and a final. By the way, when you use a burette, like a 50 mil burette that you are using in lab today, and you fill it all the way to the 0 part, the thing that people always screw up on is they go, that's 50. Do not record 50. You should record what the actual reading is on the burette. So if you fill it all the way to the top, it's actually 0.00 is what the reading should be. Should not be 50. Otherwise, your volumes will be wrong. So always read exactly what the number says when you use it. Now, you have a burette, and you also will usually have like a container, a flask, a beaker, whatever it may be. So for example, in an acid-base titration, like the one you're going to do today, you're going to fill your burette up with the sodium hydroxide, which is your base. Remember, that's sort of like your known solution, and you know the molarity of it. You'll know the volume that you're going to add. And down in here, you'll have something like HCl, for example, which is the acid. Typically, when we do titrations, in addition to say like the acid here in the beaker or the flask, we also will add an indicator. And an indicator is something that will change color when the reaction's over. And in a typical acid-base titration, the reaction is over when you hit an equivalence point. The equivalence point in an acid-base titration is the point exactly where the moles of acid will equal the moles of base. So you have exactly the same amount of acid and base added together in that beaker, and they'll basically use each other up. So basically, there won't be any limiting reagent or excess reagent. You'll have exactly the same amount of both. They both get completely used up at that point. In this example here, that would be the point where the sodium hydroxide added would completely use up all the moles of the HCl that's there. So you added enough moles of sodium hydroxide to completely use up all of your HCl. Popular indicator everybody likes to use is phenolphthalein. Spell that twice, I suppose. Yes, and phenolphthalein is colorless in acidic solution. It's actually colorless in neutral solutions, but it turns a lovely shade of pink in basic solutions. Actually, acid-base indicators work over a pH range, and something like phenolphthalein works over a pH of 8.3 to about 10. And if you're not sure about pH, anything above 7 is basic, anything below 7 is acidic, 7 on the nose there is neutral. So we use something like phenolphthalein in titrations like you're doing today. At about 8.3, it's still really colorless. And then you start to get like a hint of pink, like a super hint of pink. You got to hold like a white piece of paper up over it to see the pink. And you gradually, as you move down the pH route here, get super dark pink at this end, a nice fuchsia color. My personal favorite when I titrated, always dark pink. But actually, you're supposed to get light pink when you titrate. And sometimes your teachers will yell at you. You're looking for the first lightest shade of pink that stays. And like I said, light that you like got to hold it something underneath it, like a white paper towel or something white that you can actually just see the tinge of pink. And that's really what your goal is for. And there's really a reason for that is because the equivalence point, for example, in the titrations that you're doing today, it's like in this range, really near the colorless range of this indicator. And that's why you want the lightest shade of pink that you could get, because that should put you near the equivalence point. If you get a really dark shade of pink, you might have overjumped your equivalence point by a lot. Now, something that you will say today probably, or somebody in your lab will say today, which is a very common phrase that's always uttered when people do titration, especially for the first time, which is, I only added 1 drop and it went like super pink. Like it was colorless. I added 1 drop, it went like super pink, right? And people are like, always say that when they do titrations. Try not to laugh when somebody says it tonight. But when they do that, there is really a reason for that. You'll talk more about it in 1B, but the quick 1B version of really why that happens is if you look at pH versus, say, volume of sodium hydroxide that you're adding when you do a titration, you could create what is referred to as a titration curve, which looks something like this. And we'll just call this your equivalence point right there. And as we add base, the pH gets higher, right? And we eventually end up at the end there. So when we look at the equivalence point, and we look at when we are heading towards the equivalence point in a titration. And by the way, you'll be able to recognize this in your titrations because as you add the sodium hydroxide, it will become pink and it'll go away. It'll become pink and go away. Become pink and stay a little longer, then go away. Become pink, stay even longer, and kind of go away. The longer the pink kind of stays, probably the closer and closer you're getting to the equivalence point. And you probably should slow it up. We'll talk about that in just a second. But as you approach the equivalence point on the titration curve, you go pretty vertical, right? And when I'm going vertical on this graph, the pH here, right? And the pH here, and even my pH at the equivalence point, those are very different pHs, right? There's a big jump in pH, right? It goes from a pH down to here to a pH way up here. Yeah. And that's problematic for like your indicator because your indicator works on a pH of 8 to like 10. So that's a pretty big jump on your indicator, right? And that's why your indicator is going to go from like no color to like dark pink because you just jumped the pH, right? Now, is it really crucial? And I'll say, from my opinion, if you're really careful while you're doing titrations and your solution gets really dark pink, it's not that big of a deal if you're really, really careful. Because the really important thing when you do titrations a lot of time is you want to know the volume to get to the equivalence point, right? So when I ask you, is the volume if you ended up here, here, or here, is there a big difference in those volumes? If I draw to the volume axis there, they're all pretty much the same spot. And that's why when you add 1 drop, even though you're not adding a lot of volume, it has the ability to change your pH by a lot. And what happens is your indicator then changes color by a lot because you're now on like the 10 side of the indicator, even though in reality, you probably are pretty close to the equivalence point volume because you missed it by a drop or 2. It's not going to make a big difference in your calculation. The reason why teachers will tell you that's a crappy titration, hopefully they don't say that, but maybe they'll say that's not the greatest titration you just did there. That's too dark pink. You should do it again. Is because if you titrated like me when I went to school, I would open it up, let it all drain in, shut in, go pink, I'm done. And I was done in 5 minutes. And if you're not really careful, you could end up way over here at this pH, which is pretty much already made your indicator change. So the color you see over here would be the exact same color that you would see over here. And now if I actually was over here, did I miss my equivalence point by a lot? I did. You missed it by a lot. So if you're really careful as you're doing the titration and you really only missed it by like a drop or two, overall doesn't really make a big difference. Really, what's more important is the volume you need to get to the equivalence point every time you do a titration needs to be about the same. And then you'll be pretty good in terms of your calculation. But if you're not really careful, you really could overshoot it and your indicator wouldn't be so great. You also would obviously, in terms of an indicator, want to pick an indicator that changes color near your equivalence point. So this one works really well for titrations you're doing. But if you did a titration, for example, of ammonia, which is a weak base, and hydrochloric acid, which is a strong acid, it would be a crappy one because the equivalence point is actually acidic. And this would have already changed color or be colorless in the acidic solution, and you wouldn't be able to actually see it. Any questions on that there? All right, so back to the actual titration part of it. You're going to do a titration here. You'll know the sodium hydroxide molarity, and you'll know how much you added. You could then use stoichiometry to figure out things like the molarity of your HCl, the volume you need to reach the equivalence point. So let's take a look at sort of a titration type problem and see a little bit how it might be different and how we can approach it. So let's take a look at this one together if it ever comes. There it is. So let's just say we're going to we want to know what is the volume of 0.15 molar nitric acid that's needed to neutralize 45.0 milliliters of 0.55 molar KOH. So you can think of this like a titration type problem. It's usually when it says neutralize, it's sort of like a titration. So although it's a titration type problem, it's still really a solution stoichiometry problem, which means we still need an equation to start with. So the first thing that we want to do is have our equation, and we're going to take our acid, which is our nitric acid. We're going to react it with our potassium hydroxide, which is a strong base. So this is really a strong acid, strong base titration. This is really a double displacement reaction. So again, we're going to switch partners. We're going to make our water, right? So we're going to get H2O. And our potassium, which is +1, and our nitrate, which is -1, will come together to make KNO3. Now that we have the equation, we want to make sure that it is balanced. And I think in this particular case, we are balanced, I think, in this case. So we're good. The next thing we want to think about is sort of what was given to us. So in this case, we're looking for a volume here of nitric acid. We have the molarity given to us of it. And we have the volume of KOH given to us. And we have the molarity given to us here. So first off, we know it's really not any type of limiting reagent problem because clearly we're trying to find something of the other reactant. So it's just a basic stoichiometry problem. We also know from our previous examples, we can definitely get moles of our KOH in this case, right? Ultimately, though, if we think about the molarity of our nitric acid, we have the molarity given to us. We're looking for the volume. So the one thing that we're missing to be able to solve for it is the moles of the nitric acid. That is where the stoichiometry is going to come into play. So we're just going to do a regular stoichiometry problem so we can figure out how many moles of nitric acid is needed to react with that. And that will allow us to use the molarity to figure out the volume. So step number 2 would be to convert what they gave us into moles. We also need to convert our volume into liters. So we do have to divide it by 1,000 to convert our 45 milliliters into liters. We will get rid of our big M and use it as a conversion factor, which means it is 0.55 moles per liter of KOH. The liters will cancel, and that will give me here 0.045 times 0.55. 0.02475 moles of KOH. Now I have the moles of KOH. Remember though that what I'm really missing is the moles here of my nitric acid. So that is where the stoichiometry part is going to come into play. We can do our third step, which is our mole to mole relationship, And from the equation, we see 1 mole of nitric acid gives us 1 mole of potassium hydroxide. So we will use that to do the third step. And we'll take our moles, 0.02475 moles of KOH. We're going to do a 1 mole of KOH to 1 mole of nitric acid. That's going to give us 0.02475 moles of nitric acid. With that, we now have the moles of nitric acid that we need. We were given the molarity. So our fourth step here is actually using molarity on the back end to solve for volume. So we're going to use our molarity here on the back end to solve for volume, which means liters would be moles divided by molarity. So we just calculated the moles. We're going to use the molarity here of our nitric acid that was given to us, and that is going to be 0.15 moles per liter, or a liter is 0.15 moles. In this case, I actually want moles to go away, so I'm going to use it in the right version there. And we're going to put liters up on top, 0.15 moles on the bottom. Those moles will cancel. So we're going to divide by 0.15, going to give us 0.165 liters, which if we want in milliliters, a liter is 1,000 milliliters. That's about 165 milliliters of nitric acid would be required in this step. So in this case here, we actually used molarity in both spots, the second spot and the fourth spot, and we're able to figure out the volume needed to neutralize it. So for example, if we were doing a titration like this, and we started with 45 milliliters of that KOH in the beaker, we would have to take from our burette 165 milliliters of the nitric acid to reach the equivalence point. That's basically what that number means. Question on that. Now, why we have this one here to finish up on a variety type problem of this, or variable type of problem, which is what happens if we wanted to figure out like the molarity of it, right? Like you're going to do in lab today. So let's just say we did a titration of, there are 45 milliliters of our same guy here, 0.55 molar KOH with, or it took titration of that to reach the equivalence point of a titration. We'll do 35 milliliters of nitric acid. So let's just say it took 45 milliliters of our KOH solution to reach the equivalence point in this titration. We want to know what is the molarity of the HNO3. All right, so I'm going to just kind of steal some of this stuff here since we already kind of have it done. We obviously would have our equation we would need to do like normal. We would need to convert into moles like we did here like normal. And now if we think about our HNO3, we have 35 milliliters of it. We're looking for the molarity, which is moles per liter. So we do have the liters part. We just need to convert it into liters, obviously. We will still do our mole to mole relationship, which means we do have the moles, right? Just like we did previously. So we have our moles, which would then be our top part here, right? So now if I wanted the molarity of my unknown acid would be the moles, which would be 0.02475 moles, divided by my volume that I used, converted to liters, divided by 1,000. And now I can figure out the molarity in this titration, which is very similar to what you will be doing today. And if we did it in this made up example, we'll see how I did. It means that the molarity of my nitric acid in this example would be 0.707 molar in this case. So again, that's a variation of this, very common in a titration problem. You actually only know the volume of your acid, for example. You'll use stoichiometry to figure out the moles. Moles divided by the volume will give you the molarity of your unknown acid. Any questions on that there? Yeah. In lab, step number 4 would actually be this version of it. This would be like your step number 4, because at that point you will know, for example, in the first titration, you're adding 20 milliliters or using 20 milliliters of your acid. You're going to add water to it. It doesn't matter. You're still the 20 milliliters is actually the volume that you want to use. So you'll know the volume of the HCl. After you do your titration, you'll know how much volume of sodium hydroxide. You can then do the stoichiometry part to figure out the moles of the sodium hydroxide, then the mole relationship to the HCl. And then at that point, you'll have the moles of the HCl, the volume of the HCl you started with, convert that to liters, divide them, and then you'll get the molarity. So the last part here is pretty much like the calculation you'll do in lab. Yeah. Other questions? All right, we'll lay it up there for today.